let's say, 5 formulas now for doing integrals. And there are 5 of you in this room. Don't count. Don't count. It's roughly 5 of you in this room. So what are the 5 integral formulas that we actually know? So actually, what's one integral formula we know? Yeah, the log rule. So the integral of 1 over x dx is? Yeah, the natural log of x. All right, so that's one. Karina, what's another one?
The e.
Yep, we've got e. So e to the
X.
yeah, just e to the x dx is what?
E.
Yep. And then what's another one, Mario?
Yeah.
Yeah. No one said the simple one yet.
X to the n.
Yeah, x to the n. So the integral of x to the n dx is
over n plus x. X to the exponent n plus x.
you mean n, right?
N plus 1.
Yeah, 1 over n plus 1, x to the n plus 1. All right, there's 2 more that we know. One we learned last time. Well, both of them we learned last time.
Is the like 1 over n and then something.
Is it the other e one?
Yeah.
Yeah. So the integral of e to the nx dx is 1 over n e to the nx. And you'll notice this is actually the general formula for this one. Because what happens if n equals 1? Then that's just e to the x. And if n equals 1, 1 over 1 is just 1. And if n is 1, that's just e to the x. So really, this is just a special case of the general rule that we derived at the end of last class. Okay, so that's what we have so far. We have 4 rules so far. What's the last one? Or what's the last 5th technique? It's the major technique we learned last time.
X negative 1 dx.
No, that's this one. X to the negative 1 is really 1 over x. It was the whole lesson of 3.4. We learned a whole method called Yeah, you. Yeah, you. Yeah, you. Yeah, you.
Yeah, you.
U substitution. So that's it. This is what we have so far. These are the only integrals that we know how to take. And this last one is incredibly diverse because we're allowed to take a whole bunch of integrals that don't look like these 4, and we're still able to do them by translating the integral into the substitute variable u and then integrating that. So to kind of motivate the u substitution again, we wanted to note that we can't really do much with these first 4. There's a whole lot of other formulas out there we'd like to integrate. So u substitution is a way to translate other looking integrals into one of these 4. So that's why u substitution exists. And u substitution is technically what? U substitution, well, that question might sound a little vague. U substitution is technically the chain rule backwards. That's what u substitution is. It's really just the backwards chain rule. All right, so I'd like us to notice that. Here's an example. Let's say I wanted to take the derivative of the formula, the derivative of, we'll just say 2x plus 3 to the power of 40. So I'd like to take the derivative of that. So I would do the chain rule, which would be, well, that's not a very fancy one. I'll do 2x squared plus 3. There we go. So the chain rule would say the derivative of the outside, leave the inside alone. So I still have 2x squared plus 3. And then multiply by the derivative of the inside, which in this case is 4x. So there, that's the chain rule. And let's say that I gave you this integral. So now I'm giving you the integral. Let's see, 40 times 4 is 160 x, and then 2x squared plus 3 to the power of 39. There, so now I'm suggesting let's take the integral of this. Now obviously, what answer should we get? if we want to do the integral of this, we should get that as the answer, because the derivative is the forward direction and the integral is the backward direction. So now that we've done the chain rule on that function, if I did the integral, I should get back here. And so we did u substitution by, what did we let u equal? What was normally our choice for u?
Using the inside.
Yeah, using the inside function. So we would want to look for whatever we might consider the inside function, which would be there. So we'd say let u equal 2x squared plus 3. And then what did we do? After we chose our choice for u, then what? What would we do?
Derivative.
Yeah, take the derivative of that. So now we'd have du equals the derivative of 2x squared is 4x, and we'd have to put a dx next to it. And the derivative of 3 is 0. Okay, so now we have this, and we would go ahead and move that coefficient over to the other side. So we'd have 1/4 du equals x dx. And why did we do all that? Yeah, to plug in, to substitute. So if we go back and look at our original formula here, we do have a 2x squared plus 3 part right there that we can plug into u. And I do have an x dx term right there where I can plug in a 1/4 du. And then I can translate that integral. So let's do that. I'll move it to the left a little bit. I'll bring the 160 out front just to get rid of it. And then I've got an x dx, which I can replace with 1/4 du. And I've got 2x squared plus 3, which I can replace with a u. And now I do have a simple integral. So that's how the chain, or this is how u substitution works. So now I gotta bring out that 1/4. So that's 160 over 4 integral of u to the 39th. And the 160 over 4 I can simplify to 40. And so that's just u to the 39th. And now we have boiled down this very complex, sophisticated integral into simply the anti-power rule. So now I can use this rule that I add 1 and then divide by the resulting number. So I've got 40 times bracket, add 1, divide by the resulting number. And look, those 40s cancel out, and I'm left with u to the 40th. So once you're all done doing the integral, what's the last thing you do with your u to the 40th? Yeah, go back to the original language you were in, which is 2x squared plus 3. So now I have 2x squared plus 3 to the 40th. And is that what we had? It is. So u substitution is what we tried last time. U substitution is essentially the chain rule run backwards. That's important. I want you to note that u substitution is the chain rule going backwards, because today we're learning another rule, which is the product rule going backwards. Okay, so u substitution was the chain rule backwards. Today's lesson is the product rule going backwards. So let's remember, what is the product rule? How does the product rule work? Let's say I want to take the derivative of f of x times g of x. What was the product rule for derivatives? Something about the derivative of the first times the second plus derivative of the second times the first. So the product rule was derivative of the first times the second plus derivative of the second times the first. Okay. Is that how we wrote it down originally? The product rule? How did we write it down? Didn't we write it down like that? Or no? No, we didn't? How did we write it down?
Yeah,
Yeah, that is. Well, so everyone start writing right about now. Let's just on a line sheet of paper is fine. Let's say instead of using this notation f of x and g of x, let's switch to using the letter, because we were already using u substitution, let's use the letter u. And we need one more letter to represent two different functions, f and g. So since we're going to use the letter u, what's the next letter in the alphabet after u? V. So we're going to use the letters u and v. So let's try taking the derivative of u times v. Folks, this is an accident of history that every calculus book will use the letters u and v. Are the letters u and v a very good choice? Here's the letter u, here's the letter v. Wow. This is a bad choice. It's a really bad choice. Which is why I will always use the cursive u, or the Greek u. I guess that's technically the letter mu, but I'll always use my cursive u and my sharp consummate V there with the sharp point at the bottom, so that we're really distinguishing between U and V. Okay, so now what would this be? We want the derivative of the first times the second. So that would be du times V plus the derivative of the second times the first, which would be dV times U. Where we continue to use the notation that the letter D means derivative. So whereas previously using notation f of x, we write f prime of x to mean the derivative. When we're referring to just letters, we use, if we're looking at u, the derivative is du. If we're looking at v, the derivative is dv. It's just another notation that means the exact same thing. It's referring to the derivative of whatever those things represent. Okay. Does everyone have this line written down? Now, we're in chapter 3, or the second half of chapter 3 anyway, and we're doing integrals. Is this an equation about integrals? Yeah. There's no integrals in here yet. We're not doing an integral. So what we'll do, folks, is let's take the integral of both sides. Let's take the integral of both sides. Wrap the right-hand side in parentheses. We're going to take the integral of both sides. So you'll put the integral symbol on the left there and the integral symbol there. This is fancy. Remember algebra. In algebra, you're allowed to do anything you want so long as you do it to both sides. So in algebra, you could add 5 to both sides. You could multiply both sides by 2. You could divide both sides by 10. You're also allowed to take the integral of both sides, and that's a valid move. That might seem weird at first, that extending the rules of algebra to calculus, you could take the derivative of both sides, you could take the integral of both sides, and that's a valid algebraic move. Okay, so what happens on the left? What happens to the integral and the derivative? Yeah, they cancel each other out. They cancel each other out, just like in algebra, if you square a square root, or if you square root the square, they cancel each other out. Right? Just a quick example. Here's x squared equals 9. If I square root both sides, what happens to the square and the square root? They cancel. Likewise, a derivative and an integral, they cancel. So what are we left with then? Over here, I've just got the product of u times v, and it equals the integral of this sum. Now, if you remember on the first day I was talking about integrals, you're allowed to break up an integral of a sum into the integral of each part. So now this is the integral, and let's write these in order now. I'm going to write v du plus the integral of u dv. Now right now we're just kind of doing algebra. I'm showing you where the formula is coming from that we're about to use. We are essentially trying to derive another formula to do an integral. And you can put a little star right here, a little smiley face. That's the integral that we want to solve for, is the integral of u dv. So let's go ahead and get that by itself by subtracting this integral over to the other side. So we're going to subtract the integral of v du from both sides. And now algebraically what we have left is u times v minus integral v du is equal to the integral of u v. And now let's write it forwards. So this is the item that we're actually interested in. So the formula is the integral of u dv is equal to uv minus the integral v. Now, at this point, you might look at that and say, Mr. G, everything you just wrote on that left-hand side of the board, I don't care at all about that. What's happening over there? What is going on? But this right here is our new formula for integrating more and different types of integrals. The only difference is that with u substitution, there was only a u. Now we're doing u and v substitution, where we're going to allow two different items, a u and a v, to substitute for different parts inside of an integral. And so this definition right here, you could call it u B substitution to just kind of extend it beyond what we did yesterday, which was U substitution. But the official name for this is called integration by parts. So that's our new formula for today. And in fact, it's our last formula. We only have a couple more chapters of chapter 3. I'm sorry, a couple more sections of chapter 3. And this now concludes the different types of strategies we have. So our last strategy is called integration by parts. And the formula is the integral of u dv is equal to uv minus the integral of v du. And technically that is the backwards it's going to tell us what something was before you took the derivative of a product. This might beg the question, if we have a backwards chain rule and a backward product rule, what else might you want? What were the 3 derivative rules? Product rule, chain rule, quotient rule. Yeah. So is there a backwards quotient rule, you might ask? Maybe. I don't know of one. I mean, technically, any quotient can be written as a product, right? So if I had a product, f of x over g of x, I could rewrite that as f of x times 1 over g of x. So technically, every quotient can really be written as a product. So we really only have a backwards product rule. We don't have a backwards quotient rule. All right, well, that was a little front work right there. That was a little front work just to give us our formula, which is u dv equals uv minus integral of v du. And we're going to use that formula today. Once again, in order to allow us to take the integral of formulas that don't look like one of these. That's what we're looking at, is we want to be able to take integrals of formulas that don't look like this. And this strategy will allow us to do it. And the strategy came from running the product rule backwards. Folks, before we keep going, any questions right now? Don, did you want me to?
No, you're good.
Oh, okay. All right. Well, where are we? Today is April 17th. So we're looking at 3.5a. Technically, we're not doing 3.5b. I believe that's not assigned to you in Math AS, and we won't do it. So yeah, we've got 2 more days. Now, next week, folks, on April 24th, I will not be here. Did I already tell you that? Oh, okay. I'm very sad to tell you. I won't be here. I would really rather be here. I hate to take a day off of school, just like you do, I'm sure, right? I don't like taking off a day, but it had to happen. There was no way around it. I have to take the day off. So you'll have a sub here. His name is Douglas Williams. Douglas Williams. He's a professor at ASU, and he's an adjunct instructor here. So he teaches at both places, math, and so he's going to come in and take right over and do chapters 3.7 with you. And I've already written down all the answers to the packet 3.7. So I wrote the whole thing out myself. I scanned it to PDF, and I'm going to email it to you guys. And then when he comes in, he'll go through all the solutions with you, so you can see it being done in real time. And then, like I said, you can look at my PDF notes. So you'll have a good time with Doug. He's a good guy. And then what? The very next day, I'll be back, and we'll do a review for that test. And then the next week, you'll take your test on Chapter 3, which is all integrals. All integrals. No derivatives. Any questions about that? Okay. I've got a joke for you. It's one of my all-time favorites. How many surrealists does it take to screw in a light bulb? First of all, have you all heard jokes about screwing in a light bulb?
Yeah.
Maybe you have, maybe you have. Well, like, what's a classic screw in a light bulb joke? I got another one. How many Zen Buddhists does it take to screw in a light bulb? 2. 1 to screw in the light bulb, and 1 not to screw in the light bulb. It's just a play on Zen Buddhism. Okay, so here's this one. How many surrealists does it take to screw in a light bulb? Fish. Because it just makes no sense. Much like the paintings of surrealists. They're just wild and crazy. Okay, well, anyway, there we go. Let's do it. So section 3.5, it's called integration by parts. There's also an integration by tables parts. I don't know if we'll get to that, but integration by parts. So here's your first example. I already said here, recall the product rule. We just did all this. And so there's the formula. Do you recognize the formula? The integral of u dv equals uv minus the integral of v du. All right? So let's try it. We're going to play around with this first one just a little bit so that we can see where it comes from here. I'll start here. So here's number one. We'd like to take the integral of 5z e to the z dz. I don't know why there's a plus c there. I think the plus c automatically showed up to be at the end of the answer. So you can just cross out the plus c. We're trying to do the integral. It's not? Okay, well then great. So first of all, forget integration by parts. Can we do this integral right now? Do we have a formula for z times e to the z? Yeah. We do? We only have a formula for e to the x all by itself. We don't have a formula for there being a variable in front of that. So no, we technically do not have a formula that does this. Furthermore, can we use u substitution? I mean, let's try. If we did u substitution, we could say let u be the inside function. Don't write this down because it's wrong. We could say let u be the inside function with a z, and therefore du equals dz. And if I plug that in over here, I would have the integral of 5u e to the u du. Did that make anything better? It's the exact same integral. So u substitution didn't do anything. You might say you chose the wrong thing for u. Maybe what you should try is e to the z is u. Well, if that's the case, then du is also e to the z dz. Boy, that's messy. And so that didn't really help us substitute in. We don't have anything to replace the z. So u substitution didn't work for this. And that's the idea. The idea is that as you move through calculus, you get to more and more complex formulas where the previous formulas that you knew don't work. So you need a new strategy. So we don't have a formula for this. U substitution won't work. So we want to try integration by parts. Okay, everybody write this down with me. We are going to choose u and v. And we're going to write it down. Let's see here. Oh, no, sorry. Not u and v. We're choosing u and v. So that's kind of our command. We want to choose a u and a dv because what you'll notice is we want to rewrite our integral to look like this. That we're going to replace some part of this with a u, and we're going to replace some part of this with a dv, and that's all we're going to be left with. We're gonna translate this integral into integral of u dv by making clever choices for what we want u and dv to be. So I'm going to go ahead and tell you what our choices are, just so we can do the integral once and see how it works. Everyone, first start by making a box, more of a rectangle, and we're going to put in u equals, du equals, and dv equals, and v equals. This is what we'll do every time with integration by parts, because we are now choosing two different things to replace with a u and a v term. But by definition, the first step is to choose something for u and choose something for dv. So I'm going to tell you our choices for u. First of all, folks, can we bring that 5 outside? No need to mess things up with having a 5 inside if we don't need it there. We want to make it as simple as possible. So we're just going to bring that 5 out. Okay, so here's what our choice is going to be. We're going to let u equal z, because that will account for this piece right there. And we're going to let dv equal e to the z dz. And that will account for that part right there. So technically speaking, if I let u equals z and e to the z dz be dv, then I've just rewritten this integral as 5 times the integral of u times dv. That was just that part. It's not very clear yet why I chose u to be z and dv to be the e to the z dz, but that's what we're doing nevertheless, is just replacing that with that and replacing that with that. Because now we can use this formula. And in fact, if we want to, let's go ahead and write the formula down. We've got 5 times this, so technically we need to put a 5 over here as well. And we can write in the formula uv minus the integral of v dv. How does everyone feel about that part? Was that Maria?
No.
Well, okay, that's true. That's acceptable. I mean, part of this is going to feel very awkward at first until we see how it works. But you definitely see the formula, right? I've got the formula integral u dv equals uv minus integral v du, and I've got it here, but I have multiplied 5 on both sides because that's what this integral was. I had a 5. Okay, let's go over to our grid. This is where most of the work happens. We're going to move down this way. So we're given the u equals z, so now we have to take the derivative of both sides. What's the derivative of u equals z? The integral of, I'm sorry, the derivative of u is du, the derivative of z is dz. So that part is done. So we did the derivative that way. Because we knew what u was, and we had to calculate what du was. Now over here, we have to go backwards. We have to do the antiderivative. You definitely want to draw those little arrows. On this side of the grid, we started knowing what u was, so we had to calculate du. On this side of the table, what dv is, and so we have to do an antiderivative to find out what v is. So the antiderivative, what's the antiderivative of e to the z dz? You'll notice we have a formula for that. The integral of e to the z is e to the z. So now I know that v is equal to e to the z. Again, on the left-hand side of the grid, we're doing the derivative working downward. On the right-hand side of the grid, we're doing the antiderivative working upwards. And now you'll notice we have something to write down for u, for v, for du, and dv. And so now we can substitute in for every single one of these parts and pieces. Was that enough? Okay.
Just a happy person.
Oh, good. I'm glad. All right, so let's try it, folks. What we now know over here is that we have 5 times the integral of z e to the z dz, which is the integral we wanted to solve in the first place. We wanted to know what the integral of 5 integral z e to the z dz is. And so we now have a formula to tell us what it is. So let's keep our 5 on the outside and go ahead and substitute for every part and piece in there. What's u? Just z. What's v? E to the z. And then minus the integral, what's v? V is e to the z. And what's du?
Easy.
Just d to the z. There, dz. So our original integral is now equal to that. And I claim this is a good thing because this first part is simple. It's already done. It's not even an integral anymore. It's just a variable times e to the z. So that has now technically been integrated. It's outside of the integral symbol. And how about this one? Can we do the integral of e to the z dz? Yeah, we have a formula for that. It's just e to the z. So now what we have is 5 times the integral of z e to the z minus e to the z. And so technically, we're done. Because there's no more integral symbol anywhere. We've finished the integral. And so going back to the original problem statement, the integral of 5z e to the z dz is equal to 5z e to the z minus 5 e to the z.
That's it.
Yeah, that's it. Yeah, that's it. Now, that might have seemed like a lot of smoke and mirrors. But the key was that we had this formula, the integration by parts formula, that allowed us to write our original integral as the difference between a non-integral and a simpler integral. Would you agree that this integral here was easier than the original integral? Is that fair to say? That this integral was easier than the original one? It is easier because this one we have a formula for. It's one of our basic formulas. Whereas this one, there's another variable in there. We don't have a formula for doing it. So technically, we took a hard integral and rewrote it as the difference between a simple product and an integral of an easier integral. That's what integration by parts is all about. Rewriting a hard integral as an easier integral. In fact, that's what the purpose of u substitution was as well. The purpose of u substitution was to rewrite a hard integral as a simpler integral in terms of u, and that's what this process gave us. Now, are we right? Oh, and by the way, plus c. Are we correct? Is that really the integral of this? Is that what's in the back? That must be the wrong answer.
2.
Yeah, the answer can't just be 2. I wonder what that's referring to. I must have given you an answer key to something else. Yeah, don't.
Numbers.
What's that?
Numbers, like infinity signs.
Okay, yeah, no. That's the answer key for the other part, 3.5.b. I'm sorry, there's no answer key right now. But forget the answer key. Oh, it's in the middle. There we go. So what is it?
5 times g times dz.
Isn't that what we got?
Yeah, they just broke it.
Yeah. They just left the 5 outside?
Yeah.
So they got this answer. Okay, good. So that is the answer. So says the back of the book. How do we know it's the right answer?
Smart.
Okay. How can we check the answer?
Do that.
We do the derivative. If we take the derivative of this, we better get the original formula. So you don't have to write this down, but watch. If I take the derivative of 5 z to the ez minus e to z, I'll do this one for us. I keep the 5 outside, and I'm going to do the derivative. This is a product, so that's the derivative of the first times the second, plus the derivative of the second times the first, minus the derivative of that one. And what that gives us now is e to the z plus z e to the z minus e to the z. And notice what happens to my e to z's. They cancel, and I'm left with 5z e to the z. Is that the original expression? Yeah. So integration by parts did work. Integration by parts allowed us to take a complex integral that we did not have a formula for, and u substitution did not work. And we were able to do integration by parts. Now, one thing I'd like you to write onto this grid, because this grid is actually really important. This is the main thing that we're writing down for every problem. Notice on the left-hand side, where we did the derivative, we started with our choice of u, and when you take the derivative, you need it to get easier. So I'm going to put a little note here that when you take the derivative of your choice of u, it has to get easier. So notice, would you say that z becoming a 1 is easier? The derivative of z is just 1 dz. Is 1 easier than z? I mean, is it less complex? It is. And then on the other side, when you do the antiderivative, you need it to get not worse. Okay? And since we started with e to the z and we still have e to the z, it didn't get worse. So folks, I want you all to write that down. That when we do our choice of u and dv, because that's what we're going to do every time, we're going to choose a u and dv in the very beginning. whatever choice you make for u and dv, you need to choose those two parts of this integral such that the derivative of u gets easier and the antiderivative of dv gets not worse. It can be the same, it just can't get worse. And that's really important. We're gonna return to that over and over again. Okay, that was the first integration by parts problem you've done. Right now you probably feel uneasy, maybe confused, a little nauseous, anything along those lines. So let's do another one and see how it works. So our second one, oh, well this one is very identical to the first one, but we'll try it anyway. So we've got the integral. Can we go ahead and bring the 6 out?
Yes.
6x e to the 4x. In fact, you know what we could do with that 6? We can leave the 6 all the way alone and just do integration by parts on this, and then at the very end, multiply our answer times 6. Is that fair? So folks, I'm just going to get rid of the 6. I want to simplify it so we can just focus our attention on the integration by parts process. So there's our integral that we want to do. And draw your grid. We need to choose a u, and we need to choose a dv from there. Well, there's really only two parts to choose from. You've got the bit that's x, and you've got the bit that's e to the 4x. So I want to show you what I mean by, on the u side, the derivative should get easier, and on the dv side, the derivative should get, I'm sorry, the antiderivative should get not worse. So again, I'm going to tell you what the right choice is. The right choice would be to let u equal x. That would account for this piece. And then let dv be the other piece, which is e to the 4x dx. I claim those are good choices. These are good choices because, first of all, if I make those my choices, then right now I can go ahead and call this u dv, which means I can go ahead and enact the integration by parts formula and go ahead and say that that has to equal uv minus the integral of v du. So far that's the main point, is to choose to chunk that into two different pieces. One piece we'll call u and one piece we'll call dv, because then we get to use this formula. So in order to use this formula, we need to know what u is, what dv is, what v is, and what du is. So that's why we have a grid. We go over to the grid now and let's find out what all those other parts are. So on the left-hand side, we need to take the derivative and we hope it gets easier. So what's the derivative of u? And what's the derivative of x? Dx. So yeah, it did get easier. Where there was once a variable, now there's just a dx, or if you'd like, a number 1. You don't really need the number 1. On the other hand, we need to go up now, taking the anti-derivative, and we want it to get not worse. So what's the antiderivative of e to the 4x? We have a formula for it. What's the antiderivative of e to the 4x? 1/4 e to the 4x. So let's write that down. So the antiderivative of dv is v, and the antiderivative of e to the 4x dx is simply 1/4 e to the 4x. Now, I claim that's not worse, right? I mean, a coefficient is never worse. A coefficient just comes along for the ride. It didn't make it harder. It's just a coefficient that will come along for the ride. So we've done it. These are now going to be the parts and pieces that we plug into integration by parts. So let's do it. On the one hand, our choice of u and dv was x e to the 4x dx. And indeed, that's the integral that we wish to solve. That is the integral we wish to solve. And now we continue plugging in. Our choice for u was x. Our choice for v is 1/4 e to the 4x. And see, that's why that 1/4 didn't make it worse. Just plugging in a 1/4 right there is no big deal. The 1/4 will just be up front. Didn't make that harder. And now the integral of v du. So v is 1/4 e to the 4x. And du is 1 times dx, which is really just dx. Now let's just pause and notice what we've got here. We wanted to solve this integral. This integral does not have a formula that we know. A new substitution wouldn't work. So we chunked up this hard integral, and I'll go ahead and say this was a harder integral. And we chunked it up into a choice of u and dv, which allowed us to make this grid and calculate a derivative and an antiderivative. And now we get to use this formula called integration by parts. We plugged everything in. This part's already integrated. It's just, normal algebraic expression. And this integral, take a close look at it, this integral is easier than the original. Why is this one easier than the original? Because what? Yeah, the 1/4 you can certainly bring out front. And then you're just left with e to the 4x. Do we have a formula for e to the 4x? Yeah, we do have a formula for e to the 4x. So this integral is going to be easy to do because we have a formula for it, whereas this integral was harder. We didn't have a formula for it. And that's the whole point of integration by parts, is to take a hard integral that we don't have a formula for and to rewrite it as the difference between a regular algebraic expression and an integral that's easier to solve. So let's just rewrite this again one more time, pulling the 1/4 out. So we've got the integral of x e to the 4x dx is equal to 1/4 x e to the 4x minus 1/4 the integral of e to the 4x dx. All I did there was bring the 1/4 out to the front, just so it's a little cleaner. And now, what's the integral here? That's minus 1/4 times, what's the integral of e to the 4x? 1/4 e to the 4x. And so we have 1/4 x e to the 4x minus that. And other than cleaning it up, we're done. All the integral symbols are gone. That means we have successfully taken the integral of the item on the left-hand side, and we just have an algebraic expression now. So the integral of x e to the 4x dx is 1/4 x e to the 4x minus 1/16 e to the 4x.
When do we put in the 6?
Now we would put it in the 6. Very good question, because originally we pulled that 6 out front. So if I wrap this whole first thing in brackets, so I'd say, okay, I want that thing, but actually that thing times 6. This thing is equal to that thing, so I would wrap that all up and put a 6 on it. And now that's genuinely the answer to the question that we were doing. I brought that coefficient back at the end. So what's our answer? The integral of 6x e to the 4x dx, which is the original problem, is 6/4, which is really 3/2 x e to the 4x, minus 6/16, which is 3/8 e to the 4x. Does that match the answer in the back? Well, they didn't reduce it? What did they put it as?
6/4.
Oh, they have 6/4 and 6/16? Oh, okay.
Well, they have 6 and 4 to the power of 2.
Oh, really? Okay, so it's massively not reduced. Okay. Well, our solution is reduced, and it looks nice. So that's the answer. How do you feel about that? Would you say Daniel lost?
Lost.
That's okay. We'll do more. At what point did I lose you? What, Kristen?
So once we started.
Once we started? Okay, go ahead, Daniel.
Yeah.
Okay, well, maybe we should take a big picture view. Now that we've seen this process twice, we can really look at it and reflect, Luis.
And how do you do the 140?
Where? Here? Because in my grid here, our choice for dv was e to the 4x dx, and we have to go up to get a thing for v, and the antiderivative of e to the 4x was 1/4 e to the 4x. Yeah. I mean, this grid is very important because once we choose a value for u and dv, you have to take the derivative to get du, and take the antiderivative to get v, and then those are all the parts and pieces that we substitute into this formula. Yeah, so this formula is really important. It's called the integration by parts formula. And if you look at it, how many different items do we have in this formula? We have a u, we have a du, we have a v, and we have a dv. So that's 4 objects that we need in order to plug into this formula. And those are the 4 objects that we put in this grid. You get 4 objects by starting with the 2 that you originally chose, and then calculating the other 2 through derivatives and antiderivatives. Okay, those were good questions. Ask more, Adon.
So you pulled out the 1/4, right, on the right side. Yeah,
Yeah, I just pulled the 1/4 out.
and then how do you get another 1/4?
Because what's the antiderivative of e to the 4x?
Oh, okay. That makes sense.
Okay. Okay, good. Yeah, folks, this is
So
good.
the integral for the top of the integral and bottom.
Wait, say that again?
That same one, the integral of the e to 4x, and that's the antiderivative.
Yeah, that's the antiderivative. Yeah, in fact, it's the exact same antiderivative. We did it up here once, and we did it down here as well.
And then you just multiply the 1
We
together.
multiplied the 1/4 together to get 1/16.
Okay.
Yeah, at this point, you'll notice over here there are no more integrals. It's just algebra. And so now we're just simplifying. Okay, those are good questions. Elias? James? Wendy? Rena? Anna? And how's your baby?
Good.
Oh, good. Is he asleep right now?
I hope so.
We can only hope. Yeah, okay. All right.
Just a quick question.
Yeah.
Just to make sure, you took up the 6 in the beginning just to make it easier?
I was just pulling the 6 out in the beginning so that we wouldn't be bogged down by it. Because when you do an integral, you can pull that out, the 6 out, and then just do the integral, and then keep the 6 outside and bring it back at the end. Yeah, I mean, technically, by bringing that 6 out front, I could have left it out in front the whole time. It's just that when I finally get down to here, I'm saying, if I'm multiplying this formula times 6, then this side also gets multiplied by 6. Right, the formula for integration by parts, if I multiply the left-hand side by 6, the right-hand side gets multiplied by 6. And that's why at the very end, I multiplied the right-hand side times 6. So that it would be part of it. Yeah, we didn't have to. We could have left the 6 in there all along. And maybe my desire to make it less complicated actually made it more complicated by thinking, what are we doing with the 6? What's that, Daniel?
Oh, no.
Okay. All right. Now, before we move on to the next one, I'd like to show you what a bad choice for u and v would look like. So I'm still going to look at this problem right over here. And let's just say that I started the whole problem. And again, you really only have 2 things in here. You've got an x and you've got an e to the 4x. One of them is going to be u, and one of them is going to be dv. Folks, how do you feel about that part? The integral only has 2 pieces.
Is the u always going to be like a variable?
That's the thing. No, there's no hard and fast rule. But thank you for asking that. Either one of those pieces is going to be the u or the dv. You don't know which is which. Just because it's written in front doesn't mean it's going to be u. You just know that if you have 2 parts that you're looking at, one of those parts is going to be u and one of those parts is going to be dv. And so really, how many different choices are there? You either make x be u and that be dv, or you make x be dv, or you make that be that. So how many different choices are you really looking at? You've got 2 options, right? One of those options is going to be successful, and one of those options is not going to be successful. So let me show you not successful. What if we had the integral here of x e to the 4x, and what if I chose, okay, so everyone watch very closely here. Here's my grid, here's my u, du, and here's my dv, my v. What if I chose to make x be dv and u to be e to the 4x? Do you see how that's different from what we chose originally? Originally, I chose to let u equal x and dv be e to the 4x. So I've switched those. And remember, my suggestion is that when you do this derivative, what should happen? It should get easier. Okay, well, let's look. The derivative of e to the 4x is, that's the antiderivative, 4 e to the 4x. That's the derivative. Whereas, what's the antiderivative of x? You'd have to add 1 to the power and then divide by the resulting number. So v is going to end up equaling x squared to the 1/2. Did that get not worse? It's supposed to be not worse in that direction. Is 1/2 x squared worse than just x? Yeah, this is worse. We now have a quadratic, not just a linear term, we have a quadratic. So this choice of e to the 4x here and x here is a bad choice because it got worse over here. And this didn't even I mean, it didn't technically get easier, it stayed the same. Now, just to show you how bad this is, if I write down the formula, which is u dv equals uv minus the integral of v du, okay, keep watching. This is really important. This is really important. This is why we do it in this way. This one is simply x, no, because I need to write down my choices of u and v. This is really e to the 4x and x. Well, what do I have now over here? U times v is simply e to the 4x times 1/2 x squared. And that's fine, because that's not in an integral. So that can be whatever, right? Because it's already done. It's just an algebraic expression. But look now what I have in the integral. Now in the integral, I have v, which is 1/2 x squared, times du, which is 4 e to the 4x. Look at this integral. It's definitely worse. It's worse than the original. The original was merely x e to the 4x. Now I have x squared e to the 4x. This derivative is worse. It's more complicated. And I'm even less prepared to deal with this integral than I was the original integral. I definitely don't have a formula over here for x squared e to the x. So that's what happens when you have a bad choice of u and dv. Your original integral gets worse. And so then you stop, you scratch it all out, and you switch back to your other choice of u and dv. All right, well, let's try another one. Okay, great. We're gonna, I just need you to have a little scratch, go back to your notes, your scratch sheet of line paper. And we're going to do a really fun integral. In fact, this is a classic. And I will give you bonus points on the test. This will be a bonus question. I'm telling you right up front, it's a bonus question. If you can do this on the test, you'll get bonus points. One simple integral formula you might want to have is the integral of the natural log. Notice that we don't have that formula yet. Do we have a formula for the integral of the natural log? No. And notice at this point, your brain might be turning to mush, because what we do have is that the integral of 1 over x is equal to the natural log of x. And the derivative of natural log of x is 1 over x, but what we don't have is the integral of natural log of x. And so I'm curious, what is that? Because this is, I mean, that would be a very natural thing to want to ask. What's the integral of natural log of x? Well, we have no formula for it, so let's see if we can find it. Let's find the integral of natural log of x. First of all, again, do we have a formula for the integral of natural log of x? No. Could we use u substitution? I don't think so. U substitution wouldn't work. You could try, but it wouldn't. Integration by parts might work. So let's try. Go ahead and make a grid. And we're going to have to choose a choice for u and dv, and then take a derivative to get du and an antiderivative to get v. So what should our choice of u and dv be? First of all, do we even have two things in this formula? I mean, yeah, technically there's a dx and then this, but are there two separate pieces over here? Not including the dx, are there two things over there? It's just one thing. But what invisible thing is sitting in front of that natural log? A 1. So there are actually two things. And so we can choose one of them to be u and one of them to be dv. So which should be which? Should we put natural log x here and 1 here? Or should we put 1 here and natural log here? Let's try this one first. What's the derivative of 1? 0. Well, that's nice. I mean, that's very simple. But what's the antiderivative of natural log of x? Remember, the antiderivative means integral. What's the integral of natural log of x? We have no idea. That's what we're trying to solve in the first place. So we actually have no idea what that is. So that can't be our choice because we have no idea how to do it. And plus, if there's a 0 in the formula, that would cause one of these formulas to go away. That would be a 0 right there. So the whole thing would be 0, and the formula might not work. Okay, so what should we do instead? Let u equal natural log of x, and let dv equal 1 dx. So that will be our choice for splitting this up into a u and a dv. By the way, folks, have you noticed that in this formula, whenever there's a d something on the left, there's always a d something on the right? That always has to be the case. Same thing here. When there's a d something on the left, there has to be a d something on the right. Okay, so let's split it up. Our choice for u is natural log of x. So that technically there's my u right there. And my choice for 1 dx is my dv. Normally we don't write it that way. We would write it down as u dv. So that's the beginning of our formula. So let's write down the entire formula for integration by parts. The rest of it is u v minus the integral of v. There. That's how that happens. Okay, what do we do now? We have to go up to our grid and finish calculating all of these things. What's the derivative of natural log? What's the derivative of natural log? Yeah, 1 over x dx. And what's the antiderivative of 1? What's the antiderivative of 1? Let's go back to our formula. 1 is really 1x to the 0. So how do I take the antiderivative of 1x to the 0? What do you do with the power anti-power rule? You add 1 to the power, and then divide by the resulting power. So our answer is just x. All right. So that's, now we have all 4 pieces to put into this formula called integration by parts. So on the left-hand side, our u dv is simply natural log of x times dx, which is good because that's what we were hoping to find was the integral of natural log of x. And now u times v would be natural log of x times x. U times v, natural log of x times x. It's traditional to write the x first, followed by the natural log of x. We put the natural log of x at the end. Minus the integral of v. What's our v? Simply x. And what's our du? Ooh, 1 over x dx. Now, is this integral easier than the one we started with? Because that should always be the case. If we do integration by parts correctly, the integral you start with is slightly harder. The integral you're ending with is easier. What's x times 1 over x? Not x. It's just 1. x over 1 times 1 over x. The x's cancel, and that's really just, yeah, minus the integral of 1. And we just said that a second ago. What's the integral or antiderivative of 1? Just x. So now we have x, natural log of x minus x. That's what the integral of the natural log of x is. Now that wasn't a problem in your packet, but it is a new formula that we want to write down to go along with all of our other formulas. So now we know we have another formula that the integral of natural log of x is x natural log of x minus x. Now again, this is just another formula to know and memorize. We now have the anti-power rule, the 1 over x rule, the e to the x rule, the e to the nx rule, use substitution, integration by parts, and now we have this rule that we can use for future reference as well. What do you think, folks? Do you need a reference sheet for the test?
Yeah.
I agree. I think this is a lot to memorize, and it's more important to be able to use it than to memorize it. So I will make you a reference sheet that has all of these formulas on it, and then on the test, it's just a matter of applying it. Does that sound okay?
No.
You're not upset by that? Okay, so that's the integral of natural log of x. Again, are we right? How do we know if we're right? You take the derivative. So watch, and maybe even do this one, because for extra credit, I want you to show me the derivative. Let's take the derivative now. What's the derivative of x natural log x minus x? Let's check that the derivative of this really is natural log. So the first thing is what? First we have to do the product rule, because we have a product and we want to take the derivative of it. So the product rule goes like this. It says the derivative of the first times the second plus the derivative of the second times the first. So the derivative of the first, what's the derivative of x? 1 times the second plus the derivative of the second, what's the derivative of natural log x? 1 over x times the first, and then that's done with the product rule. So now what's the derivative of x? 1. So what do we end up with? We have 1 natural log x, which I'm just going to call natural log of x, plus 1 over x times x. Once again, that's just 1, and then minus 1. So the 1's cancel out, and you're left with natural log of x. I would write all that down. I'm telling you right now that that's going to be my bonus question on the test, is show me how to take the integral of the natural log of x, and then prove to me that your answer really is the integral by taking the derivative of it and showing that you get natural log of x. All right, so still to do is number 3, 4, and 5. I didn't realize I kept 6 and 7 on there. You can actually cross out 6 and 7. 6 and 7 I won't test you on. But we will go ahead and do 3, 4, and 5. But let's take a break. Time is 12:06. Let's come back at 12:16.
You just look too quick.
Yeah.
Barely like.
Mr. J.
Yeah.
I have a question like way off topic, but you know how right now you did like you're gonna be doing a record sheet for this test.
Yeah.
And then at different times before you had like some formulas up. For the final, will we have those
Yeah.
as well?
Yeah, I think that sounds fair.
Okay, that. We just need the pizza. Yeah, I did. I just want to add like 2 episodes.
No, like I'm like, yeah.
I want to explain. I thought it was easy. I just
You school?
and then I don't know if you have it. See it? Because you have to apply some for it. But then it was easier there because of the questions. They're like right there next to the computer, so you just have. Oh, because if you're a friend, you're gonna sign up, but you don't have to sign up. And after that, that's it.
You can just pay for it.
You just if you haven't put any information for it. You're gonna put it like since last time. Well, I mean, it's online.
Wait, isn't it?
I don't know.
I'm thinking of I'm gonna crush on her, but then you pick.
Then you can mark it as say like it's the
But I think my well, it's fun. It's really fun. Really so fun. That's why. I think we don't. That's I think I'm making the same. Yeah, you just have to like actually do it. Like, I know it's everybody in math class, but every last thing to do it. I did it. Yeah, like they book the assignment and stuff like. At least that's on my business class on school. I'm so. I'm good.
Me too.
It's fine. I just did. Oh, you have to come. But even if you didn't say it, that's not. Like I wasn't trying to help you.
Yeah, I know this. Okay, well, I don't know. I don't know if it's just a part of it. Okay, so the lemma, like,
That might be the baby.
I feel like because it's kind of like maybe we'll hear for some way and for some type.
That's just, go ahead and repeat the explain.
Yeah, she's gonna be on one. So, I'm like, that's what I'm like, for the first one, so some of it. I heard it's just now. We got so chunky, I don't know. I looked at him the other day and I'm like, because he was from straight chunky. I did not know that he hates showers. The other day, he took him a shower. And he was trying like a good poetry.
Oh. Yeah, I think I have a lot of time. When he goes with
He will not pay. That's an old thing right there. He got really red. I think it's really. And then the other day, I was changing him. It was nighttime. And I noticed that he got sleep. His clothes and his such everything. Which is really good. Apparently, I guess it was dark, sleeping, I didn't notice. Put on his comfortable. And I didn't notice until the next day all the way over. Why is this clothes on the wrong way? And I looked and it's just like you notice the pocket of his back.
Yeah.
And I'm like, no wonder it's ridiculous. One of his boots on the bottom. But he didn't realize that the foot is more. This is so sad. Good thing I wanted to be it's just that's when I need to go class at 11 because I'm doing Tuesday once a week. This is like those times I finish one. What are they? Everything is Yeah. They let us into
I didn't really I just feel like
I was excited. Only, I just everybody was excited because they know I wasn't working.
I didn't really get this.
Yeah. I was so stupid. It was extreme. And the person, I wasn't look at the regular person. I didn't have to stuff. I don't know why this anyway is better. It doesn't sound. Mm-hmm. It's really tricky. And then,
Never
well, yeah. With the eyes on that one. Really. Yeah, I really think it's weird.
What is
Like, how do you like the shoes? They're just shoes. It's really a match, but just you can see how blue I am. It's gross. That's why I'm not to look What? Yeah, I don't know when I got close. It was very pretty. But then you turn and you know what's on people were pleased. If he didn't feel ours is different from then 0 to 3 months. Only if they stretch that he doesn't. He only took some 3 and 6.
like people should know that
They gave me like extremely when you're born again with them.
I just don't
I can't feel like you should know. Okay, good.
All right. Let's proceed. We'll do, I believe, just two or three more examples of integration by parts. Then maybe we'll have some time to look to the next day. So, we'd like to do integration by parts. Whoop, no, I'll leave that. So are we all looking at number 3? All right, so for number 3, we'd like to take the integral of the natural log of 5z plus 3. Now, do we have a formula for the integral of natural log? We do now. Yeah, we do now. We just did it. So, but for our natural log formula, what has to be inside the natural log? Just a single thing, just a single variable. And we have more than that. We have quite a bit more than that. So this is an interesting problem because we can do u substitution first to replace the 5z plus 3 with a single u. And then once it's been replaced by a single u, we could do integration by parts. Well, we don't even have to do integration by parts. We can just use this formula. So let's take a look. This one's fun because we're going to do first u substitution, where, remember u substitution, we choose the inside function, so u is going to be 5z plus 3, and so du is going to be the derivative of 5z plus 3, which is, derivative of 5z is 5, derivative of 3 is 0, so it's just 5dz. And as always, with u substitution, we move that 5 over to the other side, so we have 1/5 du equals dz. So now we can go ahead and do u substitution up here. So our new integral is simply the natural log of u, and we replace the dz component with a 1/5 du. So now we have 1/5. So that was the u substitution component. Notice that both of these strategies, u substitution and integration by parts, the goal is to replace a complex integral with an easier integral. That's always our goal, is to make our integrals easier. And now we can make it even easier by bringing out the 1/5. And now we simply want to take the derivative of integral of the natural log of u. Now do we have a formula for that? We do. We'll just replace all the x's in this formula with u's. And so now we can say the integral of natural log of u is going to be 1/5 bracket what we said the answer was, which was u natural log of u minus u. Notice at this point is the integral is still there. The integral is gone. We've done the integral. So in fact, that's the end of the calculus portion of the problem. The integral symbol is no longer there. At this point, this is just manipulation of algebraic expressions. So at the end of u substitution, what do we always have to do? We have to go back to the original expression. So now we have 1/5 times u, which is really 5z plus 3, natural log of 5z plus 3, minus 5z plus 3. And that's it. That's the end of the problem. We successfully took the integral of the natural log of 5z plus 3, and we did that in two processes. First, we did u substitution to break our integral down to something that was a little easier to do, something that we had a formula for. And then we used our formula that we just came up with to replace the integral of natural log of u with u natural log of u minus u. And that was the end of using our formula, which was technically integration by parts. And then we just go back to the original variable by letting u equal 5z plus 3. Yeah, so we really didn't do integration by parts in that problem. I suppose we could have, but we had already derived this formula. So there's no need to redo that whole problem since we've already done it. Thoughts about that one? Certainly not as long. Folks, sometimes being exposed to it the first time, the first day, it's really muddy. I mean, that's how it goes for me. Every math class I have, I read the chapter before I go there, and then I listen to the teacher, and then I go home and I reread the book again. And then sometimes I reread the book again. And then finally it makes sense. I mean, that's the process. Sometimes the first glance, you're seeing it, you're writing it all down, but it might take some repetition. So for instance, just as clarification for all of you, I hope you know that later on when you go to do your Math AS, take a look. Here is your chapter 3.7 3.5a homework. And here's the question. Oh, here. Yeah, there. This is the one we just did. Natural log of 3s plus 1 ds. So when you go home to do this problem, First of all, you can probably just look at the beginning of our problem and look at the end of the problem and see how the answer goes. I hope you don't do it that way. I mean, clearly you can just use that as a formula for typing in the answer. That it really doesn't help you learn. But what you could do is now you could go home and watch this video too, because now this instructor is going to show you another way of solving this problem. Only difference is they're actually going to do integration by parts on the whole thing. And we did it by using a formula. So there's a little difference there. You might still watch it just to see what you gain from it.
Those videos aren't you.
Oh. I'm me. Yeah, no, it's somebody else. All right. Well, that was that one. Let's try another one. This next one, number 4, is integration by parts. So we'd like to find the integral of 2t squared natural log of t. First and foremost, what can we do with that 2? If everyone's okay with that, I'm going to bring the 2 outside. I just focus on doing the integral of t squared times natural log of t. Oh yeah. Well, you know, we can write the 1 and the e for the whole rest of the problem, but we're really only going to do that at the very end when we actually have to plug it in and then subtract using the fundamental method of calculus. So yeah, I mean, this is the problem 1 to e. We could probably focus on just doing the integral for now and then go back in and write all the 1 to e's, or we can write the 1 to e's now either way. Thank you, Mario.
Is that the same thing as the 2?
Yep, I'm just going to wait to do it until the end. Because right now we have the bigger job of actually doing the integral. So folks, notice first of all that if I just had t squared, could we do that integral? If I just had t squared, it would just be the anti-power rule. What about if I just had the natural log? Yeah, we have a formula for that now too. So see, if I have just one of them, I could do the integral no problem. But the problem is that we have a product of 2 functions. And that's what makes it more challenging, that we have the product of 2 functions that I could do alone, but cannot be, you know, I can't use these formulas to do the product. Someone who didn't know calculus might be tempted to say, hey, let's just break that up and say the integral of a product is the integral of t squared times the integral of natural log of t. Wouldn't that be nice? But that's not how it works. You can only break up an integral over addition, not multiplication. So this naive thinking doesn't work. If it did work, we'd be done, right? I mean, you can just do the integral of t squared, then you can do the integral of that, then multiply them together. You'd be done, but you can't do it that way. And that's why we have integration by parts. Integration by parts allows us to do this integral when we don't have any formulas that give us that. So let's begin by making our grid. And we need to make a choice for u and dv. Because the beginning of the problem is always the integral of u dv. So what should be our choice for u and what should be our choice for dv? Remember, we only have 2 things. We have a t squared and we have a natural log t. So we're either going to put the t squared here and the natural log t here, or we're going to put the natural log t here or the t squared there. So it's just a matter of choosing which one of those arrangements is better. I think that's a good choice. Let's take a look. This way we're doing the derivative, and we want it to get easier. And this way we're doing the antiderivative, and we want it to get not worse. Now, oftentimes you might just want to try both. Try both and take a look at it yourself. Sometimes you have to try both, and you don't even realize it until you get to the end. You're like, oh, this didn't work out. Let me go back and try the other way. So sure, let's go ahead and try first putting the natural log of t here and the t squared here, because Mario suggested it. Does anyone think this is the way that it's going to work out? It is going to work out. This is the right way to do it. Yeah?
Then I had a question because when we did the bonus one, you said something about if it has dv, then the other part should be.
Oh, you're right. You're right. I'm sorry. This is the other part. The dt is coming with it. Thank you, Anna.
Okay.
Yeah, the dt has to come with. Because after all, we have to replace all of this with either the u or the dp. So you're right. The dt goes down there with the t squared, and the natural log of t is up there. Thank you, Anna, for clarifying. All of these things have to come into the grid somewhere under u or dv. All right. Well, let's go ahead and do the derivative part. What's the derivative of u? Du equals the derivative of natural log of t? 1 over t. And did that get easier? Well, I think so, because the natural log went away. Now we just have a variable of t. I think that's better than natural log. And now how about the antiderivative? Well, the antiderivative of dv is v. The antiderivative of t squared is what? What's the power rule say? Add 1 and then divide by the result. So would that be t cubed with a 1/3 out front? Now, right there, you might say, Mr. G, I feel like that's worse. Because we went from a t squared to a t cubed. And you'd have a valid point. That does appear to be worse. This one appears to be easier. This one appears to be worse. Now, what you might consider, and you guys don't have to write this down, but consider the alternative. What if we had chosen the other way around? What if we had said that u was t squared dt and dv was natural log t? Oops, dt. What would have happened then? Going this way, definitely easier. Because t squared became 2t. But on the other hand, the antiderivative of natural log is that whole nasty thing. So what about that? Was that not worse? Which is worse to you folks? Is it worse for t squared to become t cubed or natural log t to become t natural log t minus t? Which is worse? You know, out of the two terrible alternatives, which one is worse or worse? This one is worse or worse. That one's worse or worse. It's worserest, right? Compared to this one. Now, which one was better? I would say getting a natural log to turn into just 1 over t is better news than just a t squared becoming a t. So overall, it might not be obvious at first that this is the better choice, but it is the better choice. And sometimes the only way to see that is just to do both alternate realities and compare them both. All right, well then now let's do it. Let's write down the formula for integration by parts. The formula for integration by parts is u dv equals uv minus the integral of v du. And yeah, as Mario and I mentioned, we're going to leave the 2 alone for a while, and we're going to leave the 1 and the e alone, and just focus on doing the integral. And then later on, we can go back and focus on the fact that there's really 2 out front. There's really a 1 and an e there. So the integral that we're trying to solve is u dv. I'm going to erase all this so we don't look at it. Which is d squared natural log t dt. Now we just have to multiply u times v together. So u was natural log t, and v was 1/3 t cubed. And then we're going to subtract the integral of v du. There. Did we plug all that into the formula correctly? U was natural log t, v was 1/3 t cubed, v was 1/3 t cubed, and du was 1 over t dt. Is that what everybody got? Notice that once you make your grid, It's just a matter of plugging those 4 pieces into this formula. Right? The formula is the bedrock. We're going to use this formula. And so once you choose which part is u and which part is dv, you do your grid to get all the other parts, and then you just plug them into the formula. And then you start simplifying. So this first part, if I put it in order, that's 1/3 t cubed natural log of t. Because fractions always go in front and natural logs always go at the end. And then here, I will bring my 1/3 out front. And then I just have the integral of t cubed times 1 over t. What's t cubed times 1 over t? What happens with that t in the denominator? It cancels with one of the t's in the numerator. So that's just t squared dt. Now, going back to the original idea, remember the whole idea is that the integral you start with, which is complex and hard, after you use the formula integration by parts, you should get an integral that's easier. And is it easier to take the integral of t squared than it is to take the integral of t squared times the natural log of t? Yeah, for sure, that got easier. So what is the integral of t squared?
1 over 1, 2, 3.
Yeah, 1/3 t to the third. Notice there's a 1/3 floating out in front, as well as the fact that t squared, you add 1 and then divide by the resulting power. So that gives us 1/3 t cubed natural log of t minus 1/9 t cubed. And that is the integral of t squared natural log of t dt. That's the indefinite integral. That whole answer that we came up with is just the indefinite integral without the upper and lower limits of integration. So we still have to go back and do the upper and lower limits of integration and evaluate. And we still have to multiply the whole darn thing by 2 because we took the 2 out in the very beginning that we were waiting to bring back at the end. So maybe you need more space, or maybe you just move over to the right. Now I'm going to, let's integrate now. Well, we've already integrated. Let's evaluate from 1 to e. Wasn't that the problem we were doing? So to integrate from 1 to e means that once you take the integral, it's going to be 1/3 t cubed natural log of t minus 1/9 t cubed. We're going to evaluate that from 1 to e. So you put that big evaluation line at the right-hand side. So remember, the integral symbol at the left, and then after you do the integral, the evaluation line to the right. And now we get to plug in e into all that, and then subtract, plug in 1 plugged into all that. So it's going to be something minus something, where here you plug in e, and here you plug in 1. Now, this is definitely the job for your calculator. It looks like a bummer of a job to plug into all that. So you have some choices. You could always use your graphing calculator and type in the formula in and of itself. So like, for instance, watch me. I'm just going to plug in the formula, 1/3 x to the third times natural log, 1/3 times x cubed times natural log of x minus 1/9 times x to the third. So this is what my formula looks like. Well, what the graph looks like. And so now I want to know what that will equal if I plug in e. Does anyone know how to make a table of values? Oh, a table. But now how do I make that? Ooh, maybe I can copy and paste the whole thing. Well, that's clearly not working. Okay, I don't know how to do it. Too many variables. What? Well. All right, I thought I was going to be able to have a nice way of just plugging it in. On your graphing calculator, you might just have to go through the process of actually typing it all in. But use a lot of parentheses so you can go back and replace the E with a 1 later on. And keep in mind that E is, well, no, you just want to use the letter E on your calculator. I don't want to say that this is terrible to type in your calculator. It's just very lengthy. So 1/3 times E cubed. Oh, you have to use so many parentheses. There's natural. What did anyone get for the first one, plugging in E? Did anyone get 4.46345? Then if you go back and plug in 1, oh, got a syntax here. I got -1/9 right there. So then 4.46345 plus a 9. 4.5756. Now that's not the answer yet. All we did was evaluate that from 1 to E. What do we still have to do? We still have to multiply that answer by 2. So now, what was that answer? Yep, that, and then times 2. So now it's a matter of checking our answer in the back is it equal to 9.14912?
Yes.
Oh, thank goodness. All right, well, folks, so that's a lot of work. It's just a lot of work plugging it into your calculator because it's so painstaking. Okay, well, me oh my, we didn't even get to do the last one. And now time is up. So you know what I think we'll do? Because I don't want to get behind, and when you come back into class on Thursday, I want us to start where we left off. I think what that means is I'm going to take that last one off. Will you guys mind? You're very upset?
I am.
Okay, I'm going to take off number 5. So on the homework in Math AS, there's actually just 4 questions to do. And for this particular unit. And the number 5 and number 6, they're worth 0 points. So you'll still see them, but you don't have to do that.
Heartbroken.
Okay, that's all set. Oh, that's all right.
Did you pass their test?
Good. Didn't I give you your test back last
Oh,
time?
did you pass it?
Oh, did I pass my test? Yes, I passed my test. Thank you. Thank you for asking. All right, folks, we're all done.
So, sorry, you said that we are not.
Oh, yeah, correct. So, folks, lots of things to say. The next couple pages, you can take the whole next assignment called assignment 3.5B, and you can take it and tear it out and put it under your pillow for some future days when you want to do that. Or you can tear it out and recycle it. Yeah, no, we're not doing 3.5B.
Can I see the actual like work done? Like
On my calculator?
yeah, I guess. Well, like, what did you plug in? Like, how did you?
No, we're not doing that.
Oh my gosh, my calculator only goes back so far.
I think it's
Okay.
gone from 4.5 to 9.
Okay, you want to see?
Yeah. And then I.
So I want to plug in E.
Yeah.
Well, unfortunately, E, when you call it up, you can only call up second ln, which is e to the 1. So you're always going to be typing in e to the 1.
Yeah,
So let's watch. I'm going to do, we're starting right here. So that's parenthesis 1/3 times t cubed, which in that case is e cubed, which really is e to the first, there's e to the first,
yeah.
and I have to take that. So now e to the first is all in parentheses and cubed. Now that's e to the first. I took e to the first and put it in parentheses, and that's being cubed, and then I close the parentheses. So how many left parentheses are there? 1, 2, 3. How many right parentheses? 1, 2, 3. Okay, so now that so far that's just 1/3 e t cubed now times natural log of e to the 1. Again, the natural log of e to the 1. So there's parentheses, 2 left parentheses, 2 right parentheses. Okay, now minus parenthesis 1/9 parenthesis times the same thing I had up there, which is e to the first times 1. So that's parenthesis, parenthesis, e to the 1, parenthesis, parenthesis, parenthesis. That's the 1/3 e cubed times natural log of e minus 1/9. Oh, I didn't cube the e yet. There. So that gave me the 4.465. Now what I'm going to do is go back in with that whole same expression, but I don't want e to the 1 anymore. I'm going to delete the e to the 1, but that'll give me parenthesis errors. I need to get rid of one more parenthesis as well. So again, I get rid of the e to the 1. I have to get rid of the parenthesis. I'm going to delete the e to the 1 and delete the parenthesis, because I still need my left parentheses to match my right parentheses. So that gave me negative 0.11, which if you hit the math track button is negative. And that's a double negative, so you're really adding that thing plus 0.11, which is that, and then it has 1. Did that work?
Yeah.
Anna, when I see you, I'm so excited to ask about you and the baby, but I also acknowledge that not every day was wonderful.
No.
You know, I don't mean to put any pressure on you that every day you're gonna be like, yeah, Mr. G, it's awesome, because in fact, some days,
Some days they just wanna like, you're just like,
yeah, some days are really, really hard, and I get that. So I'm sorry. I'm all enthusiastic to ask about your